Agricultural engineering. Okay, that's also my field. The last sentence I couldn't understand. Ah, abiotic stress on plants. Okay. Like drought stress? Ah, okay. I have something for you.
Good morning. My name is Abel, and I am a tourism specialist. So now I'm doing ecotourism
Oh.
and coral tourism, and I'm quite interested in diversifying the products of the farm of my family. So very interesting.
Okay, so even a private interest. Okay.
My name is Joseph. I graduated here from philosophy,
Mhm.
but now I'm taking a master in environmental management and ecotourism.
Also ecotourism.
It's the tourism.
Okay, let's see what we have for you. And you? Your interest is? Okay, sustainable agriculture. Okay, good topic. So, and your interest, I think, all know here, or would you like also to introduce yourself?
I work here at the university at CIGRAS as well, and I think my background is on plant physiology, plant biotechnology, yeah, in some way coordinate this exchange with
Okay, fine. So I think I didn't forget anybody here, and let me take down the tone maybe to not be disturbed here anymore. So, okay. Yeah. So first I will give you some introduction here, and I titled it Water, Food, Energy, Climate Nexus. So many people talk about water, food and energy nexus meanwhile, because those things are combined. But I have found, okay, also the connection to climate here is very important, and let's see how some aspects of this nexus is working and why our Earth system is under stress and what we can do coming from our various disciplines we just have heard, like agricultural engineering and arts and philosophy and ecotourism. Well, first I have to give you some words about our university, and so I start with the world and I show you the origin of our university. You know that I'm coming from Germany, but the origin of our university is here, and by far this is not Germany, this is Indonesia. And you might wonder, why is the origin of a German university in Indonesia? I can tell you why. Because there are also volcanoes, like your volcanoes, and it was Tambora who exploded here, a large eruption here in 1815, and a lot of global dimming by all the dust in the atmosphere, by far more than when your volcanoes here are exploding. This was really a global effect, and people in Europe, they didn't know what happened, but there was the next year without summer. So it was a natural climate change very suddenly, and it was a summer full of rain and low temperatures, and there was no harvest, and there was a food crisis over there in Europe. And people reacted. There have been riots. In France, there have been really violent riots in Baden-Württemberg, the part of Germany where I'm coming from. The ruler was very wise, and he invested in agricultural education. So, okay, let's do more for the farmers, better education to increase yields. And so in 1818, it was the start of our university. And so this year we are celebrating 200 years of existence. And so you see how those events have global impact. Yeah, now finally we see Germany. So in Middle Europe here is Germany, and Baden-Württemberg is part of Germany, and Stuttgart is the capital of this state of Germany, and there is our nice university in this castle here. This was the castle of the ruler who also started agricultural education. So a quite small university with 10,000 students, 150 professors, and that's about my chair here. My chair is in agricultural engineering, especially in tropics and subtropics, because Hohenheim has long-term relation to those countries to fight against those food crises since the time it was founded. And in my group I have 3 subgroups, 3 assistant professors who are working in these different fields of water, food and energy, and therefore our field is quite wide here. In water we work about water saving irrigation methods, and I will show you some examples how water can be saved in irrigation. And we are developing sensors to measure water status. And again, I will show you examples, what we are doing precisely there. We are working on food, especially on post-harvest technology. What is coming after harvest? How to preserve food, how to keep the value of the food, or even to increase the value by certain processing steps. And we are dealing with waste reduction, because a lot of this food is lost coming from the field, going to market. A lot of food is wasted. And finally, energy, and there we are working on bioenergy, how to use those wastes to produce bioenergy, and we are working with solar energy, how using the sun for all those purposes in agriculture, mainly in post-harvest technology. And so we have projects, let's say all over the world. Of course, we also have projects at home. We also have German projects. We have in Europe, Albania, but many projects we have in Asia. Large projects here, long-term projects here in China, in the very east and the very west of China, here in Thailand. In Malaysia, you will see examples. In the Philippines with the IRI, with the International Rice Research Institute. And in Africa, Tunisia, and here Ghana, Nigeria, Kenya, Tanzania, and now coming here to your area here. And it's just recently, so maybe, so I would say 2 years ago, there have been no red dots on our map, and we thought, we have to make more again in South and Middle America. It's also tropical, it's also our mandate region. And you will see we have now activities in Colombia about milk cooling, and recently here in Puerto Rico, a project also about biorefineries. And recently you also can find the red dot here in Costa Rica, because we have now a common PhD student, Catalina. We are waiting for her in Hohenheim, and this is the start of a very close cooperation between Hohenheim and Costa Rica. Okay, so, and from those different locations I will show you some examples, but also give you some background about this nexus. I have put it like a pyramid here. Water, food, energy and climate is connected. And there are several connections, and we could brainstorm if you would like. I will just show you some examples from my field why those things are connected. For example, water and food, because in many places we need irrigation water for food production. Maybe not so much here in Costa Rica. You have a lot of rain, but if you're producing greenhouses, you need irrigation, even here in Costa Rica. And when we are producing food, we are also producing emissions to water. Because fields are fertilized, and those fertilizers are leached and at the end are ending in the water bodies. And just one example, yeah, how these two nodes are connected. Or the next one, food and energy. What are the relations between food and energy? For food production, we normally use mineral fertilizer. We do not so in organic farming, but most of the food products are produced conventionally using fertilizer, and you need a lot of energy to produce nitrogen. Very high energy input for nitrogen production. And on the other hand, if we are producing food, we are producing biomass, and we can use the wastes to produce energy, to generate energy. And in some cases, the plants are especially grown with no other purpose, just to produce energy. Meanwhile, energy crops like miscanthus, or sugarcane, Brazil. Yeah, we have a visitor from Brazil producing alcohol from sugarcane. So that means instead of producing food, the harvest goes to energy production. Yeah, and then you see here a competition between food and energy, because biomass can be used for both purposes. And this was very severe in 2008. There was a bank crisis, financial crisis, and the prices have been rising before this crisis. Oil prices have been rising, and so also food prices have been rising in the same way. Because either you can use the food for producing energy or to feed people. And so you see there's a very strong relation between food and energy. Or the next one, water and energy. Yeah, with water we can produce hydropower, like you here in Costa Rica, building dams and then using hydropower to produce electricity. On the other hand, if you want to irrigate, you have to pump water. And for water pumping, you need energy. Or here, what about energy and climate? When we are producing energy with fossil fuel, conventionally, with oil, with coal, with gas, then we are causing emissions here. We are increasing the CO2 content of the atmosphere. Yeah, the climate change effect. And on the other hand, climate is governing the cooling demand. So we have everywhere aircon, and the higher the temperature, the more energy we need for air conditioning systems. Another example here, that's a very natural one, between climate and water. Yeah, we need the precipitation, we need rain from the atmosphere for plant production here. And on the other hand, we have evaporation here from plant canopies here, where water goes back to the atmosphere. That's a quite natural cycle here. One more here, between food and climate here. Yeah, if we produce food, we have a land use change. We don't longer have forests, now we have plant production, a different land use, and therefore we also change the climate by this land use, because we don't catch so much carbon as a natural savanna or a natural rainforest if we have plant production. And we need here the atmosphere, the climate here for photosynthesis. It's solar radiation, it's temperature, all what we take, all what we need to produce food. Okay, so you have seen some examples, maybe you have better ones, there are much more I know, just to explain why those things are interlinked, and if you turn one screw, the other ones are also moving. Yeah? It's a connected system, you have to be very careful what you are doing. Okay, some background data which you know here. This is population growth, the blue one here, yeah, population is growing 7 billions in American language, or milliards, mathematically more correct. Still growing here, maybe flattening in the middle of our century, but still growing. But the green one maybe is not so much familiar to you, and this is the rural population. And you see that the rural population is not growing, it's stagnating. So people are going more and more here to the cities. That means we have an urbanization. More and more people are living in cities. So we have a lack of labor in rural areas, and we have to feed more and more people in cities. That means we have to process the food so that you can transport it, so that you can store it for days or weeks or months until you reach the population in the cities. Okay, so when population is growing so tremendously, also food production has to grow. We have to feed these people. And if we look to our agriculture area, we are maybe a bit of surprised. Yeah, we see over the years here the arable land, here the brownish or red line here, and we see this is stagnating. We see that the pastures might have grown a little bit, but now also it's stagnating. We need see how the forests are decreasing, because always a bit more land is used here for arable land and pastures. And we see that the irrigated land is a bit increasing. Not tremendously, but increasing. How can we feed the world, the growing world population, by stagnating areas? And those lines are stagnating because we don't have more fertile land. All fertile land is used already. And the free land, the forests here, they are hard to cultivate, luckily. Okay, we see that indeed we are producing more food. These lines here are increasing here for maize, rice and wheat over the years. Production is steadily increasing. We even have here an overproportional increase of maize. Later I will explain you why. How can that be? Area is stagnating and the production is growing. How? It's a question to you. How can that be? How can we produce more from same land? More yield by more inputs. That's the story. More yield. That's my next slide. Those are the yields. Now we have here the yield in tons per hectare. Again, maize, rice and wheat, and you see all those curves are growing. And those curves are growing by more inputs, better varieties by plant breeding, pesticides, fertilizer, irrigation, to produce more from the same land. And that's why we can still feed the population. And here we see now example of maize. For what purpose we are producing maize. And then we see the red line. So we are producing maize mainly for animal feed. First we are feeding animal and then we are eating the animals. And for food, it's also increasing here, the green one, but we see here the blue one, and those are other uses beside feed and food, and this is energy. Because starting in the 2008 years here, we have here this inclination here. We have here more production of maize for bioethanol, for example, in the US. But also in Germany, we are too small to be too much visible in those global charts, but in Germany we have a lot of maize production for biogas, for example. Okay, this here is energy production, not food production. And then we see the losses here. Those are post-harvest losses, and they are also growing. They are still increasing, and we could save this amount and use it in a better way than just losing it. And why do we need so much feed here for animals? Because we are rearing pigs. You see the red curve here? Those are pigs. So a lot of meat production, pork. Cows are also increasing here, but not so tremendously. And hens, we have here thousands of hens, these figures. It's also increasing. People are changing the diet. People are using more animal proteins, and this is shown in the next slide here. We see Here the left scale protein in gram of protein per capita and day. And we have on the right hand the energy, the kilocalories per capita and day, which are available for the world population. And you see in terms of energy, it's really rising here, going to 3,000. So we are going to a luxury consumption, yeah, maybe depending on body weight, 2,000 would be enough. Yeah, and we are going here towards 3,000 kilocalories per capita and day. In average, of course, there are people which have much less, and there are people who even have more than 3,000. Yeah, and about the proteins, we see that the animal proteins are rising, still lower than the vegetal proteins here in green, yeah, but this is more stagnating, and here proteins from animals here are rising. And it's much more expensive, also in terms of energy, to produce the protein from animals than from plants. Yeah, but the trend is going in this direction. And this is why our system, Earth system, is under stress, because more people changing the diet, also producing energy from biomass, and this is creating stress. We see here maybe a more complex chart here. On one axis we have the population per arable land in capita per hectare. That means how many people do we have to feed from 1 hectare. And the other axis here is the irrigated area in percent. And I have taken the figures from 1960 to 2010 for the world globally. This is the black line here, yeah, lying here, starting here with 1960 and here the year 2010. Again, a question to you. What is the story of this line? How would you interpret this line? What would you tell me about the line? What's the story behind? Just explaining the chart. Again? Yeah, might be a matter of the green revolution here that started in the 60s. That's right here. Yeah, and also irrigation is part of the green revolution. So we have here an inclined line, goes to the right upper end here. That means if we go up, what's happening when we are going up? We have more and more irrigated land. This is one part of the story. And when we go from left to right, what does it mean, going from left to right in the chart? More population. We have to feed more and more population per hectare. Now it's, from the side I cannot see it exactly, a bit more than 4. Bit more than 4 people per hectare. It was 2 in the 60s. So, and now we are looking to different regions in the world. Yeah, we are looking to Asia. Asia is here. What does it mean when Asia is here? What would you say? Yeah. Correct. So we have much more people in Asia, very densely populated. Here, meanwhile, we have to feed in Asia here 8 people per hectare, more than the 4 in the global aspect. Okay, and the reaction is that more and more land is irrigated. 40% is irrigated, mainly rice production, to feed people in Asia. And if we take out China from Asia, then we are here. And we see extreme conditions. In China, we have to feed 12 people per hectare. Fertile land. China is a large country, but many, many areas are deserts. You cannot produce food there. Food production is really limited to some fertile areas in China, and so we have to feed 12 people per hectare. And you see the inputs are very high, more than 50% of the land is already irrigated. And I have just one example more, and nitrogen fertilizer. Same game. The same axis here, population, people per hectare, and we have here the nitrogen fertilizer in kilogram per hectare. Here is the world, global figures, and we see in the average in the world we have here a bit more than 50 kilogram of nitrogen per hectare. How much nitrogen per hectare do you fertilize here in Costa Rica? We have some agronomes here. Any idea how much nitrogen, pure nitrogen, N per hectare? 150? Do I hear more? Up to 200? Do I hear more? No. Up to 200. Let's have a look to Asia. Started at the bottom line here in the 60s before the Green Revolution. Yeah, and then inputs have been increased. Okay, rising here in Asia, we have now a bit more than this 100. Looking here to China, yeah, we see here values going up to 250 kilogram of nitrogen per hectare. So immense inputs, yeah, and this nitrogen is also going to air. We have measurements in China, and there is a gain of nitrogen by rain in some areas of 50 kilogram per hectare. A present for the farmer, of course. You don't have to pay for that, but for nature, it's really a tragedy. Yeah, if all the free land is irrigated by rain with such a high load of nitrogen, then you are changing the ecosystems. Yeah, okay, but it's not a China bashing here, just to show you what's going on worldwide here and how people are reacting to produce more food per hectare because we cannot increase the hectares we have. Okay, let's come to water. Some figures to water. I have also other things than figures, but we need a little bit of base, yeah, the arguments behind. And here we see water withdrawal in cubic kilometer per year. I think nobody can imagine cubic kilometer, 1 kilometer in each direction. A huge cube. And we have different colors. We have in the bottom line here, we have the agricultural water use. We have yellow, the dams. We have gray, the industrial water consumption, and we have blue, the municipal water consumption or domestic water consumption. Yeah, that's what we are drinking, what we are using in the household. And you see how the curve is really rising here. Yeah, not so fast here then in the last decades. And you see most of the water is used by agriculture. And the yellow parts are also very interesting. Dams, what does it need? What does it mean? How can dams consume water? Maybe you have an idea? Building dams, maybe for hydropower, using the water also for irrigation, and how can those dams consume water? Very interesting aspect. By what? Exactly, by evaporation. I was very astonished. I found this figure just recently, 1 year ago, which is now in the statistics of FAO. Yeah, those are artificial water bodies. And those water bodies have evaporation, and this is now meanwhile counted by FAO. You see also here that the gray bars are growing more than the others. This is industrial water use. And of course the blue one, because we have more people on the globe, and people are using more water meanwhile. It's a matter of lifestyle. How much water is consumed, you will see it in a while. Okay, so you see here the distribution and the competition for water in between those sectors. And industry is very rich, very strong lobby. And here I would say, in agriculture, I wouldn't say that we consume water. In agriculture, I would say we use water. It goes back to the natural cycle. Rather, we dilute it or we spoil it by agrochemicals. Then I would say, okay, then it's not the same quality and we are wasting water. Otherwise, I would say, okay, we irrigate, but it goes back in the cycle. Not so in the industry. If it's polluted and just a carrier to get rid of certain substances to the rivers, to the sea, then this water is really consumed, really spoiled, yeah, not longer for human use. Okay, let's see these shares in different parts of the world here. Let's go to Europe, and you see that in Europe we don't need so much water for irrigation, we need the water here more for industry. And in Africa there is not much industry, so most of the water is used for irrigation. Asia, even more here, yeah? But if we go to absolute values, yeah, then we see here again the water withdrawals, again our cubic kilometer per year, and we see that Asia is using the most part of water because of high population, yeah, high inputs in agriculture. You see the green bar is the biggest here. Yeah, this water goes to agriculture. Followed by the Americas, and finally by Europe and by Africa. In Africa there is not much water use here. Then not so densely populated, rain-fed agriculture. Okay, not so much stress on water. Here in those areas here there is much stress on water. And I promised to show you also here the water use per capita here, lifestyle. This is now water withdrawal per person in liter per capita and day. And you see it, the total water use and the municipal water use. And let's go to North America. Those are the winners. You see here, we have here a huge water use per capita. This is matter of lifestyle. In contrast here to Africa, where the water use per person is much lower. Okay. How is water availability worldwide? The dark blue colors, we have a lot of water available, can be more than 1,000 millimeter per year. What does it mean, 1 millimeter water? Funny, yeah? Talking about 1 millimeter of water. I don't know how it's in your news, in the weather forecast, how they give precipitation, how they give rainfall. In which unit? Here in Costa Rica? In what? Ah, in millimeter. Oh, okay. They're using millimeter. So what do they mean? You hear it every day. Oh. Okay, when they are telling you, okay, we are expecting 50 millimeter of rain. 50 millimeter of rain. What do you do with this information? Nothing, of course, or what? Ah, you know, okay, we rain. Okay, that would be a yes-no decision. They can tell you it will rain. Okay, thank you. But they tell you it will rain 50 millimeters. Means? Yeah. Yeah, but they have to live with what they are getting. Yeah? You cannot stop the rain and you cannot make rain. Okay, the answer to the question, okay, 50 millimeter means, okay, it's here in a height of this 50 millimeters from ground if it's catched. Yeah, if you put there a basin, it will be filled by this 50 millimeters, and that means 50 liter per square meter. If you have a basin of 1 square meter, it would be 50 liter. Those are the 50 millimeters. Okay. But you can have more than 1,000, and you see here the tropical areas, and you belong to this tropical area. Yeah, so there can be places with up to 6,000 millimeter. This is a column of 6 meter. Yeah, if nothing would evaporate, the basin would be filled by 6 meter in a year. Okay, so there is plenty of water here along the tropics here. And there are some deserts here. And they are also on the line. Yeah, this is the Capricorns here. The 23.45 degree, we will see tomorrow. You have the big deserts here in America and also Sahara, and also here in Asia, here Taklamakan Desert, where we are working, Gobi Desert, and also in the south, the same game here. We have the big Australian deserts, and we have the Namib here in South Africa, and we have here the Atacama Desert in Peru. Those are very dry regions. Okay, you have learned this at school. Yeah, this is just by the tropical circulation here. Yeah, it's raining here along the equator, and we have the dry zones here beside the equator here. Okay, what about water withdrawals? Bit different colors here. The dark blue ones are where we have low water withdrawals, and we have here the brownish and gray color here where we have very high withdrawals. And you see here this belt here, the US here, California, with this brownish color, very high withdrawals. Also here in India, here in parts of China, very high water withdrawals. Why do we have this pattern of water withdrawals in the world? Why is it so different? I know 2 reasons. Maybe you find one of them. Yeah, intensive production. Yeah, high water need. We have seen this already for the US lifestyle also. Could be a reason here because we have here low population density. What about here? India, high density. Yeah, these 2 factors, high population density, high water use per capita, yeah, lifestyle, this leads here to water withdrawals. And if you now overlap the 2 maps, yeah, availability and withdrawal, yeah, we see the relation here. Yeah, this is the withdrawal to availability ratio. And if we reach a ratio of 0.4, which means 40% of the renewable water is already under use, then we feel stress. And those are the red colors, and you see that white regions in the world here are experiencing already water stress, even severe water stress. If I go to my homeland in Germany, here in the eastern part here, there is water stress. In the US, there is water stress. In Australia, there is water stress in the press when it's really lasting for years, sometimes in Australia. Okay, but the stress is not the same. It's not felt as stress in the same way here in India and in the United States. Because if there is enough money, then people always have options. They build dams, they can buy water. So if you have a very rich nation, then the stress is not so critical than in nations where people are poor. Okay, and there are many regions here, also here in the northern Africa, where the stress is felt very tremendously. And this might change in the future. We are talking about climate change, and Costa Rica was not in the game so far until now. Okay, there's enough water and there are not so much people and you're well off in Costa Rica. But when I look to those maps, this is precipitation change to the year 2100. And in the months of the northern summer, June, July, August, this is more or less your rainy season. And we see here the red colors, which goes above -20. And then you see that Costa Rica is also here in the center of this rain reduction in the future. Yeah, maybe you have too much rain nowadays in rainy season and you are happy to have 20% less. But when we then go to December, January, February, your dry season, then we see that also here Costa Rica is in a zone where also there is less water in the future. Okay, that means also you here should think about water-saving technologies. And if you don't have to do it for your country, you have to do it for neighbor countries if you go out after finishing your studies. Okay, so now I'm going to show you some examples what we are doing here to save water. But we also decided to have a break at 10, so how strict is that? Well, they are not ready, then we continue. And maybe we can even finish the topic of water then. Okay, so what we are doing is water and energy saving irrigation methods. So if we can save water, then okay, we can produce water, food with less water, which means we also even use less fertilizer, because the fertilizer is leached by excess application of water. Yeah, and then also we need less energy for water pumping if we save the water, and then we are releasing less emissions to atmosphere. So there are many benefits if we can reduce the energy input and the water input for irrigation. And here I have 3 different irrigation technologies for you. On the left side here, I have here surface irrigation. What we are seeing in many Asian countries, here is a paddy field prepared for planting, and the basin is just filled with water, and we have a lot of evaporation and also deep percolation, and the losses are at least 40% or more. 40% of this water is lost to the ground. Okay, next technology here is sprinkler irrigation, yeah, where the water is sprinkled in the field like an artificial rain. The losses are around 20%, because most problem is wind. Yeah, there is wind drift in the field, and also if it's not leveled the field, if it's a little bit slopey, and very small slopes are enough that the water is flowing within the field, and then there are some parts which are over irrigated and the other ones are not enough irrigated, and this is counted as loss. And finally we have here micro irrigation. We just have these plastic tubes and the water is applied to the root zone, drop by drop. Yeah, this also called drip irrigation, and the losses are 10% or even below. So we have systems where we're installing sensors down at the root zone, and then we can stop the water flow when the water is going to leave the root zone. Yeah, and then we really can reduce the losses even below 10%. Okay, but most area in the world are irrigated still by surface irrigation. And also in the US, so half is irrigated by surface, not with buffaloes and those basins, but modern basin irrigation systems, and the other 50% is sprinkler irrigation. Almost 50%. There is about 4 or 5% micro irrigation for vegetable production, also in the US. Okay, that means those technologies are applied, but only to small areas, like here for olive production here, for vegetable production, for fruit production, micro irrigation systems are used. Not because they are so water saving, but because you can also apply the fertilizer very precisely to the plants. We call it spoon feeding. We are adding the fertilizer to the water, and then you can fertilize the plants very precisely. Yeah, and the rest of the land is dry and no grass is growing. It's really open here. You can go in, yeah, you can drive through with a tractor and you apply the water just where you need it here along the root zone. Okay, what about the energy input for irrigation? We see here two axes here, the flow rate, cubic meter per hour and hectare, the flow of water what we apply in a field, and we have here the pressure we need for those systems. And you see here sprinkler irrigation here, where we need a lot of pressure. We need 7, 8, 9 bar to push the water through nozzles to make this artificial rain. That means we need high pressure. On the other hand here in basin irrigation here, you don't need much pressure. You just have to lift the water from the field channel, maybe 1 meter, 1.5 meter to your field. Not much elevation. You don't need big pumps here, but you need a high flow. You are really flooding the field, and you have to flood the field very quickly. Otherwise, the losses will be even more. Okay, what about micro irrigation? It's here on the left side. So 1 bar is enough, or even half bar, to bring the water through these lines, through these black lines here for irrigation. And also the flow rate, the cubic per hour, is low because you have much time. You are irrigated all day long, drop by drop. And therefore, the flow rate is so low. And here, those hyperbolas, these curves here, they show here the power you need per hectare. This line is 10 kilowatt per hectare, this is 5 kilowatt, this is 1 kilowatt. And you see, so in basin irrigation, we are here more or less on this line here, between 1 and 5 kilowatt per hectare. For sprinkler irrigation, we are between 5 and 10 kilowatt per hectare. And for micro irrigation, we are below 1 kilowatt per hectare. That means the power which we need is much lower. And this is very important to know when we now want to save energy, if we want to use renewable energy, solar energy. And now we see here a picture from the Atacama Desert, very dry climate here. But there is water in the ground, and this water is pumped by photovoltaics. You see here the modules driving the pumps, pumping the water from the ground and filling here these high tanks. And from the high tanks it goes here in these drip lines for irrigation. If we go to this sketch, it's more clear. We have here our deep well. We have a pump down here driven by photovoltaics, filling the high tank. And from the high tank the water goes here in our system, operated by a solar generator. And this energy is expensive still. The prices went down tremendously, luckily, meanwhile, but still this energy is expensive, and you have to do everything to save energy, to reduce the power. And therefore we are applying here, of course, drip irrigation systems. But the sun is rising in the morning, is climaxing at noon and going down again. That means you have a very fluctuating energy source. And so also the water flow is fluctuating, and those systems have not been designed for that. And therefore there was first a high tank. Filling the tank, and from the tank it could go to the field in a steady flow, always the same flow. But this turned out to be the most expensive part of the system, this high tank. And we managed to remove it. We arranged here our drip irrigation system here with pressure compensating equipment here. And we could work with this fluctuating flow of water which we have over the day, and we could do here without the high tank. We did this quite early. It was in the 1980s till 1990, and in That years the systems have been still too expensive for practical application. But now meanwhile, so 30 years later here, prices went down and those systems are nowadays very interesting for agricultural production. And you see on those charts it's very well matched here. We see the year here and the daily irradiation, yeah, the solar energy which we have. Those is the blue line, and we have here also the evaporation of the plants, which is the red line. And evaporation of plants is also driven by solar radiation, yeah, by sun and by temperature. And you see that those curves are parallel. So it's somehow self-regulating. When we need a lot of water here, then we also have here a lot of radiation available. Very well matching, in contrast to lighting systems. Yeah, we have much sun in the day, but we don't need the light. We need the light during night. What are we doing when we are using photovoltaic systems? In that case, for lighting. Oh, I'm sorry, I'm talking about households. We also have, but I agree. You have, you have here so much hydropower, and everybody has electricity from the grid. That's really not a problem of Costa Rica. But in some African countries, where you have no electricity in the villages, you also would like to have those lighting system. Yeah, light in the cottage, light in the house. Okay, need a battery. You have to fill a battery during day, and then you have the light during the night. But here in irrigation, it's very well matched. Yeah? So not bad. And on this chart, we see here the irrigated area in hectare from 0 to 4 hectare here. And heat means the pressure expressed in meter. So in hydrology, we don't give it as Pascal or so, or bar, a pressure unit. We give it in height, yeah, up to 20 meter. And those lines again are the lines of same energy. And you see with the system we have designed here, we are here on this red line, and we can decide what we are doing. Either we can irrigate many hectares with low pressure, which would mean drip irrigation, or we can irrigate here few hectares, yeah, half hectare here with high pressure, which you would need for sprinkler irrigation. Yeah, and we decided to be here on the right side here to use drip irrigation and to irrigate with our system here 3.5 hectare here with 1000 watt photovoltaic energy. And when we are talking of photovoltaics, we do it later on in the day. Again, we are talking of watt peak. That means at highest angle of the sun, at noon, yeah, we can harvest this 1000 watt. Of course, when it's night, there is no energy, there is 0. This means this P here, watt peak. Okay. Yeah, but we even can do it better. Now we have seen how we can save energy, how we can use renewable energy for irrigation, but we even can save water, and that's what I'm showing you here. We call it partial root zone drying, or PRD, also now in literature for different crops. We did it in Thailand with mango. And how does it work? We have here our nice mango tree with the root zone, and there is a dry side and a wet side. We have split the irrigation system. Yeah, with strip irrigation it's very easy. You can put 2 lines left and right, and you can operate the right one and stop the left one, and then the soil will dry out. Okay, what's happening? What's happening when the soil is drying out? The roots are under stress. And when the roots are under stress, they are talking with the canopy, more or less. They are signaling There are chemical signals. Abscinic acid are produced and other plant hormones, yeah, sent to the canopy and telling the canopy, hey, we have no water, please close your stomata. Yeah, close the openings so that less water is evaporated. Okay, but the other side still has water and is still delivering water, and there is enough water to produce the fruits, because if the signal is coming, then the plant is looking for survival, investing in the fruits, not longer in the growing of the canopy. And that's what we want. In mango, that will be huge trees and you have to prune it anyhow. Yeah? Every year you have to prune it, and if you apply this irrigation system, then you don't have so much vegetative growth. Yeah? You have the investment in the fruits. And of course, after a while you have to switch. You have to irrigate the left side and dry out the right side. And in the beginning we did it just by time. 1 week left, and then 1 week, after 1 week switching. It worked, but we have been not so satisfied. It's more interesting to know how the roots are thinking about water status, and we measured this by CO2 measurement, because if the roots are active, if there's enough water, then we have a release of CO2 in the root zone, yeah, by respiration. Yeah? And we can take this as a sensor. We developed here CO2 sensors to measure CO2 content here of the soil. And when the CO2 went down, we know that now respiration is stopped, is reduced. Yeah? And then we have to switch back again. At this point, abscinic acid, for example, is massively produced as a signal for the canopy. Yeah, and what about the effect? First, to see our experimental design. We even did it very precisely with pot experiments. We have here half of the roots in the left pot and half of the roots in the right pot here, and then we could switch very precisely here and measuring the effects. We see here the yield in kilogram per tree with no irrigation on the left, 50% irrigation here on both sides reduced, and you see here 50% irrigation but with partial root zone drying, which means 100% on the left, no on the right, and vice versa after a while. And we have here the 100% irrigation. Oh, we see, yes, without irrigation there are some mango in Thailand. Yeah, so there is some rain, enough for some production. If we reduce by 50%, then we also have a yield penalty. The yields are lower here, but if we apply the 50% by PRD, there is not much difference in the total yield. And here the segments in the columns, they show the fruit size. Yeah, on top we have the large fruits, extra size, more than 500 gram. Those fruits are expensive in the market, and you see that we don't have a loss in these expensive fruits. Also the next class here, 400 to 500 here, we have no loss here. Okay, and then by selling the fruits, you have the same revenue. Yeah, you have saved 50% of water, and you have the same monetary yield at the end. What you are losing is here the small fruits here, which you anyhow discard. Okay, that was really a success, yeah, and we go on with this kind of deficit irrigation. It's still expensive because you apply it by micro irrigation systems. They are expensive, yeah, so you can afford for fruit and vegetable production. But what about in African conditions? And we showed that we also can do it by furrow irrigation systems. Here we have tomato here, and our PhD student from Ethiopia who is working here in tomato, standing here in a furrow. And here you see how the water is coming for furrow irrigation and measured by such a partial wear. Yeah, that's a measurement device to measure the flow of water very precisely. We irrigated the furrows, but we again did it alternatively. Yeah. first one furrow one day the other furrow, yeah, to also have this partial root zone drying effect, that here the drier part of the roots is signaling plant stress. And we have been eager for the results. And we did it for different varieties in Ethiopia. You see here the blue bar here is full irrigation. The next one is deficit irrigation, DI. The next one is AFI, alternate furrow irrigation. And you see, depends on the cultivar, on this Phaeton cultivar, you see that we have here more marketable fruits, even more than full irrigation. Yeah, here is full irrigation, here on the right is deficit irrigation, and there's even a higher yield. Not the same for all the varieties. Yeah, we have here some reduction here. For Corto, for example, there is no reduction if we apply it alternatively, the AFI treatment, partial root zone drying. If we just reduce the water, we have a loss. And also for this RRP tomato 2D new variety in Ethiopia, we see that we have yield losses here if we just reduce the water. If we apply partial root zone drying, we don't have significant reductions. And therefore the water use efficiency is increasing. If we have here higher yield at lower water input, of course, we have a tremendously higher water use efficiency. What does it mean? Kilogram of harvested tomato per cubic meter of water. How much marketable tomato can we harvest per applied cubic meter of water? And there's really a big difference here for all of the varieties. Yeah? So we can use the water more efficiently by using those deficit irrigation strategies. And then we continue this by looking into the quality of tomato in terms of vitamin C in this chart and lycopene on the right-hand chart. And again, we did it with two tomato varieties, but we did it now very precisely in the greenhouse in Hohenheim. And Matina is a European variety, so a standard variety. And Kochoro, again, was the best one from Ethiopia. And we compared the two. And we applied, again, here full irrigation, deficit irrigation, and PRD. Now it has been pots where we could split the roots. And it was a bit strange. So for the Ethiopian local variety, we see that we have a loss in vitamin C. So by water stress, really vitamin C was reduced significantly. But for the European cultivar, we have an increase in vitamin C. Yeah, those cultivars have been stimulated by drought stress here to produce more vitamin C here. Yeah, it's by fresh weight. Yeah. And if we go to lycopene, we have almost the same picture here. For Corocho, for the Ethiopian variety, lycopene was reduced, yeah, but yeah, it was significantly. Here is A, here is B. And for the European variety, it was significantly increased. So you have to know that you have to make those experiments variety by variety. You cannot just take any variety and then draw your conclusions for tomato. It really depends. A lot of work, of course, for scientists, yeah, to do those for different varieties. Okay. I look how much slides for water, and then we decide. 4 slides for water, Victor. Should we continue with water? We go for a break? Okay. Then let's go for a break to get also some water for us, and then we will continue. with water. And I also told you that we see some sensor systems, and one of it is infrared thermography, or IR thermography, thermocamera, and we look at the canopy. And the canopy, when there is enough water, is transpiring water, and this is cooling down the canopy, yeah, by heat of evaporation. So if you want to cool something, yeah, you can wrap it in a wet tissue. Or when we are sweating, we are cooling down ourselves, yeah, by this evaporation. This is the sense of it. And this can be measured in the canopy. Here you see such an infrared image here of a mango canopy, and you see here one leaf which is red, which means which is very hot, because we have covered it by paraffin, yeah, so that there is no transpiration. And this leaf will develop then higher temperature than the other leaves, which are cooled down by evaporation. And if there is enough water available for the plant, there is enough evaporation. And if there is water stress, then the stomata are closed and the evapotranspiration of the canopy is stopped. And this is made visible here with the thermocamera, and we have here this crop water stress index, which is then giving an index for water stress. We have here the temperature of the canopy, the real temperature, which we are measuring here beside this one leaf here. Yeah, this is the normal temperature. And then we need the temperature of a well-watered leaf. And by doing this, we also can spray it with water, and then this leaf is fully evaporating. This is our wet reference. Okay, this is the wet reference. And then down here we have the temperature of a dry leaf. This is the one which is covered by paraffin, no transpiration. This is the completely dry leaf. And again, we have here the wet reference, completely wet leaf. Okay, what is happening? Now this index is going from 0, no stress, to 1, full stress. When do we have 0 here in this coefficient? When does it go to 0? What has to happen? How can this index go to 0? Well, it can be 0 when this part is 0. When will this part be 0? What has to happen? No, just by mathematics. How can we get a 0 here for this term? When they're equal. Yeah? That means when T canopy is T wet. That means when the canopy is really fully evaporating, like a wet tree. Yeah. Then we have here a 0, and here can be whatsoever. The term will be 0. Okay, how can this term be 1? Mathematically? Pure mathematics? Yeah, when the two terms are equal. That means when here we also have the temperature of a dry leaf, when the canopy is like a dry leaf, when there is no more evaporation, then this term equals this term, and the result is 1. Yeah, so very elegant. Now this figure is going from 0 to 1, and we have now an index to identify water stress. Yeah, we can say, okay, there is enough yield production until a stress index of 0.6, for example. Yeah, you have to find out now for different plants here, how can the crop water stress index develop, still producing enough fruit. Okay. And the nice thing was that we also could apply it in Mexico, in the CIMIT, They are breeding maize and other crops, and they are interested in stress-resistant genotypes. You see here a field with many genotypes. Always 2 lines of maize is one genotype. Yeah, and now it's very difficult to measure stress reactions in such large fields and do it in the same time. Yeah, because sun is moving, climate or weather is changing over the day. So how to get real-time information all over a large field? And we could do it by climbing up here and taking thermography images here from top. And you see here the result. You see here rows with a large part of red leaves. Those are the ones who are heating up. Those are the ones who are not so stress resistant. Yeah? They are closing stomata, they are heating up, and so could be selected. And always there have been some under artificial water stress, so water was withheld, and others have been well watered, and those are the results. The black ones are the plant growth under water stress, and we have arranged it from left to right, yeah, with increasing temperature. You see here temperature C means of the canopy minus temperature air. How much was the temperature of the canopy rising above air temperature? And you see here the genotypes, and what would you say? What are now the stress tolerant ones, on the left or on the right? On the left are the stress tolerant ones, and you are right. Those are the stress tolerant. They are not heating up so much. You see, if we look to the well-watered, it's a different distribution. Yeah? But this is for CIMID not so interesting. They want to know here the genotypes which are here stress tolerant. Okay. And of course it was a bit dangerous to climb up here. And nowadays we do it now by those drones, yeah, by unmanned aerial vehicles, UAV. And I've brought one along here. It's in China where we are doing those things. Oh. Yeah, and those drones can carry cameras, and then we can measure large areas. But this research is for spraying. In China, our colleagues are using here the drones for spraying. Yeah, I have shown you that the rural population is decreasing. Young people are going to cities to earn money. And then they have a lack of labor in the fields, and now more and more fields are sprayed by drones in China already now. It's had become a business. There are small companies, and they offer to the farmers the service to come with a drone, and they spray the field, and there is a payment at the end for the spraying and for the chemicals which are sprayed. Goes together because you need special pesticide applications here, yeah, because you cannot spray big quantities as we do in conventional spraying. Yeah, going with a tractor, we add a lot of water. Yeah, the chemicals are diluted by a lot of water for spraying in the field. Here, it's highly concentrated, yeah, so that we don't have to carry too much load to the drone. It's only in the video. I started shortly again. You see the measurement devices here. Yeah, here by these test tricks here, it's measured how precisely the pesticides are applied in the field. Okay. So that was the rest for water, and now we are starting here a further topic. Now we are focusing here on food here, and I show you some examples here for waste reducing food production. How can we reduce waste in food production. And if we reduce foods, then we have also less emissions to water and to climate, to the air, because if the wastes are rotting in the field, then they are producing methane, for example, which is a greenhouse gas, or the water is spoiled if those materials are just rotting in the villages or on the fields. And if we have less waste here in food production, we also need less energy and are causing less emissions. Yeah, insects are such a problem in tropical regions. I assume also here in Costa Rica. It's here just a small list of those insects: the rice weevil, red rust floor beetle, lesser grain borer, and also some moths, almond moths, which are infesting the grain harvest. You see here such a kernel here, and the insects inside, or here just a beetle leaving the kernels, and they are lost, of course. Some beetles are just eating on the embryo, on the proteins, so they don't eat much of the corn, but the most valuable parts. And they are also leaving the feces inside the product, and it cannot be any longer sold. And you see that the optimum of development is here just in a temperature area of below 25, between 25 and 30 degrees centigrade. That's just here a tropical climate. They feel very well. The eggs are coming already from the field, and then the insects are developing. And for this situation, we developed here a so-called airtight or hermetic storage system to store the grain without exchange of air, and with a certain technology called ferrocement. You see here a steel skeleton, which is then later on covered with a thin layer of concrete. You see here the platform here, a cone, and then one cone on top. And there is a manhole on top where the grain is filled in, and there is an opening here on the bottom where you can take out the grain, a small silo. And this can be produced locally. This was in Sri Lanka. Was a PhD student from Sri Lanka. And together with him, we developed here this ferrocement bin. You see here the ready one here covered with straw for heat insulation, to prevent much temperature amplitudes between day and night. And what is then happening inside? If we close the system airtight, then we still have respiration of the cereal itself. It's also a living organism, so cereals has some respiration, but also the insects and the microorganisms. They have a lot of respiration. So they are converting O2 in CO2. And what else? In respiration. What are the end products of respiration? Water. Very interesting. Also water is produced. We had to learn. Okay, so we had here a storage period of 6 months, also to catch high prices. When farmers are harvesting, prices are low. They can harvest twice a year, and after the harvest, prices are down, and if they can store the products for half a year, they can wait for the high prices and then sell. So we took here air samples by sucking some of the air, and measured CO2 and O2 content, and you see how the O2 content, oxygen content went down, and then fluctuating, but being on a low level, and CO2 was rising, going up, also fluctuating here. Okay, and the PhD student, he went back to Sri Lanka and doing here these measurements here all this time, And then we have been very curious after 6 months, yeah, how it looks inside when we open it. And he was on phone on this very special day. And then he opened here the cap on the bottom and let out the first small amounts of cereals, and all was black with insects. Oh, he came to the phone, oh, everything full of insects. And then we decided, okay, then open on top, go up here, open the manhole. He did. He looked inside, came back to the telephone, everything black. There are insects also on top. And then we decided, okay, let's unfill the bin as we have planned, yeah, layer by layer, very carefully, taking samples, okay. And we have been then very happy that there have only been insects on the bottom and only insects on the top, small layer. And the rest was clean, very clean. This is here, this drawing, you see here the silhouette of this ferrocement bin. You see here the center, yeah, where we took the samples, and you see here in the periphery where we took samples, and we measured insect damage in the kernels, and we measured mold in the samples. And you see, okay, in the top layer there have been some insect damage and also some mold, yeah, and also in the bottom, but the rest, the lion part of the bin, was really clean, and there have also been no dead insects. If you fumigate a silo, then you also kill the insects, but the bodies are still there and are seen by the traders, yeah, and they reject the grain. But so somehow we lured here the insects to the bottom and to the top. What do you think? Why? Why did the insects go to the top and to the bottom? And by the way, on top there have been the moths, and in the bottom there have been the beetles. What is your hypothesis? Why did they move in that way? Because there is more air, okay. You have the hypothesis they moved to the area where is more oxygen. Yes. Yeah, that was also our hypothesis. And we also thought, okay, there has been some leakage maybe on the top and some leakage here on the bottom, little bit more of oxygen, and then they go there to survive. But that was not the reason. The other aspect was the reason you also mentioned, because there was more water. So we have been reading very carefully about insects, and then we learned, okay, such a beetle has a certain natural program how to move. And the first driver and the strongest one is to go down against gravity. Yeah, landing somewhere on a bulk of cereals and then going down is a very clever strategy. Okay, so this is in his program of the beetle. Okay, go down. So beetles went down by nature. And then there was still enough water and enough oxygen, yeah, to survive, to eat. And then they produced CO2. And then we learned that they go for a gradient of higher CO2, not lower. They are looking for places with more CO2. Why did nature program such an algorithm? Go for higher CO2 content in the atmosphere. Any idea? Any hypothesis?
That's where something living is breathing.
Yes, there are living others, and there we can breed and have children. Okay, yes, find partners. And then there is a third driver, and that is the higher moisture content. So moisture content is really the lacking part in a grain storage system. Yeah. So they need a certain amount of humidity in the air. And this was created by respiration, because there have been beetles active. There have been now more water in these parts, yeah, and therefore they have been attracted. So all the beetles down. The moths have a different program. They go up by nature, reaching the top of the grain bag and then flying away. So they went up, no water there, no chance to escape, they died there. But you see here the moisture content, yeah, in the grain bag, higher on top and higher down there in the bottom, yeah, by the higher microbial and insect activity, and the rest was fine. And the message is, if you want to apply airtight storage, you cannot store it with a moisture content of 14%, you have to go down to 12 or below. That's what we learned at the end. Okay, but very nice how we could lure the insects here out of the bulk and having then a nice rice bulk in our silo. That was also visible in the quality. Yeah, we have here the initial moisture content, 13.8 in the bin and in the control. Control was a very comfortable one. So in a very clean storehouse, we put bags of rice, but not airtight. Yeah? So no much effect on moisture content, but here insect damage. In our bin we had 0.16%, and in the control we had 2.46, even stored very nicely, like no farmer in Sri Lanka will do it. Yeah. Really carefully under control. And the molds, there have been some molds here also in our bin because we have applied the too high moisture content here, but in the control it was significantly more, 0.85. But germination rate was 85% in the beginning and 0 in our bin. It was still 38 in the control. And this again was a mistake of high moisture content. If you have airtight storage and a high moisture content, then you are destroying the germination capability of your seeds. Okay. One argument more to dry down to 11-12% before airtight storage. Yeah, economy was nice. We had the chance then to spread the system in Sri Lanka. And I took here 3 locations here as an example, 3 farmers, and the normal load here is this 2,300 kilogram, roughly 2.5 tons, but one he didn't fill it completely. And of course this is not the idea, because they have a very large headspace of air and it takes a long time to reduce the oxygen content. He decided to do it like that, okay. He also did not sell it at the end, he just took it for home consumption, and he just liked the nice shape of the bin, put it in front of his house to show the neighbors how nice his bin is, okay. But the others had very good success here. This one had a price by loading $0.123 per kilogram. He took the mass out after 6 months at a price of $0.206, and that was a surplus of $193 after 6 months. Well, the other one, a little bit less here, 133, with an investment of $253 per silo. So within 1.5 years, you have paid back your investment. Really a good thing. But I put it here because it's very interesting. If one is taking out rice for home consumption during the 6 months, the system is not working properly because air is going in and it's spoiled. And by the way, the beetles or the insects are not killed by a rising CO2 content. It takes a lot of concentration. You need 80% and more to kill a beetle with CO2. It was the lack of oxygen. This is what the insect is killing. Okay, let's leave a bit that topic. You also can prevent the losses in another way. I'm talking now about cassava. I think you also have it here in Costa Rica. How do you call it here? Yucara. Yucara. Okay, it's also coming from South America, yeah, it's the origin of cassava, manihot esculenta. It's well known as a tuber here. It's the staple crop in Africa. People are relying on cassava as their daily food, but it is low in protein. Yeah, you hardly can see it here. Yeah, most is carbohydrate here, a little bit of fat here, and the rest of fiber and minerals, rich in minerals. Yeah, but no protein. And therefore, we have problems in some African regions because people rely on cassava as diet. They have an overload of carbohydrates, a lack of protein. And years ago, I have seen that the cassava leaves, that ones, have a very high protein content. You see here, it can be 30% and more, yeah, protein content. And I always wondered, why don't people use the leaves together with the roots, yeah, to have also proteins? Yeah, okay, both is poisonous, by the way. They are cyanogenic glycosides, linamarin, dodaustraline, yeah, and this is poisonous for people and has to be degraded before consumption. Yeah, therefore, you have to cook cassava or to make fermented products from cassava, and the same is true for leaves. And so therefore we started to develop methods to detoxify also the leaves and to make use of the leaves. Yeah, which was not yet known in Western Africa. And mainly I worked in Western Africa, and when I was in a conference in Eastern Africa, in Tanzania, we have been in a hotel, and there was some kind of spinach for the buffet. And I took some, and I asked my neighbor in the table, who was from Tanzania, what it is, and he told me, oh, those are cassava leaves. And I was kind of shocked. I thought only we had the idea, and I have seen that they use cassava leaves in Eastern Africa for long, but they cook it for hours for detoxification. And then the proteins are denaturated and the vitamins are gone, and therefore it's still worth to work on detoxification methods. Yeah, and we do this in two projects. One is in Africa and one is in Malaysia. This one, Cassava Upgrade, is in Malaysia, and there we apply a so-called biorefinery approach. We try to make use of all the parts of cassava. We have here the cassava roots, and here we are working on a modified peeling process because the tuber has odd shape. It's not like a potato, so roundish. It's lengthy and hard to peel, and we are losing a lot of material just by peeling with a knife. So we are thinking about more intelligent peeling methods here, and we also want to extract the starch from the peels, and at the end what not can be used, at the very end at least should produce biogas at the end, yeah, to make really good use of it. And the cassava leaves here, we also want to detoxify it by different methods, mechanical, chemical, enzymatic. Yeah, we press the leaves here for the juice because most of the proteins are in the juice, and then by special processing, ultrafiltration or isoelectric precipitation, we can get the proteins and can bring back the proteins in food industry. Yeah, this would be more the industrial line, or here using the cassava leaves as they are. We are fermenting it. Cassava is fermented. In Africa it's called gari, a sour product from cassava. Do you also know a sour product from cassava here in Costa Rica? Fermented, lactic acid fermentation, sour taste. Well, it's nice. It's good. And the same can be done with leaves, and now we try to do it together, yeah, to mix cassava root and leaf for fermenting, and then having so-called green cassava with a fortified protein content. Yeah, Okay, but now some slides. This, for example, is for pressing, a spindle press. Yeah, you see the spindle here. And the cassava leaves are pressed inside. Here the sap, the juice is going out here for protein extraction, and the press cake is then used for feed and other uses. And we are optimizing the process. Oh, here you see the sap, such a green sap here. And here is a press cake. Maybe it's too much light here to see here the press cake. Yeah. And then you can optimize the conditions here, the nozzle diameter here, the speed of the screw, and then we see the effect. Yeah, if we have a small nozzle size, we go on this side here, and we have a high diameter of the press cake, which means we have harvested a lot of juice. Yeah, so we got the juice. Yeah, we have here a high amount of green juice extraction. Okay. Yeah, peeling. I mentioned peeling, and you see how much material is lost here by hand peeling with a knife. Yeah, and this is just rotting normally, just a heap. Yeah, and then rotting there and releasing methane and contaminating the environment. And we developed this peeling machine. You see it here without housing. Yeah, there is a hopper filling in the cassava tubers, and here are rotating brushes, and the peel is brushed off by these rotating brushes. I have here a video from the lab. This one was not so effective. You see, there is still a lot of peel around. It was too quick going through again, and we count how much time do you need for peeling. And later on, I cannot go forward. Okay. It shows also different pre-treatments. Yeah, we have learned that if you apply certain pre-treatments, for example, a short steam application, then the peeling process is much more effective. Yeah, here with heat application, here without. Yeah, and we have here the application time here, yeah, until 90 seconds. And here the peeling time, you see peeling time has not such a big influence, but here the application time or incubation time here, yeah, and if you go here to the left side and then apply 4 minutes of peeling, this is quite long of course, then you can peel off here the cassava tuber properly. A further improvement is to apply certain enzymes, yeah, to degrade the cellulose and hemicellulose of the peel. There are certain enzymes available, and you see here a scan of it by electron microscope, and you see how the structure here is changed here. Also, even visually, you see how the peel is looking after those enzyme treatments, and this is now our most favorite way to go. Yeah, steam application requires energy here. Here enzyme application might be more economic at the end, and we just remove the peel and not the starch body which we want to use from cassava. Okay, so now we are coming here to a further topic, energy reduction in food processing, yeah, applying less energy in food processing. And here I brought some of our latest research here. It's about solar milk cooling. We are using photovoltaic energy for milk cooling. Many farmers don't have access to electricity. You are here blessed here in Costa Rica. I have learned that all of your farmers have access to electric grid and can use it for milk cooling. Not so in many parts in the world. like here in northern Africa. This is Tunisia with our freshborn postdoc, Victor Torres, who just defended. And he is standing here beside this photovoltaic array here. It's a double system here. You see 2 refrigerators in the background, and you see here funny milk cans. And I have to explain what we are doing here. These milk cans have a certain inner cylinder here, and this cylinder will be filled with ice blocks. We are producing ice blocks in a refrigerator, placing the ice blocks here in the cylinder, putting the cylinder in the milk, and the milk is cooled down in the can. The last one was a prototype can. We have learned we should use original milk cans, as farmers are accustomed to. Here is the original milk can. Here, this cylinder, which is put in the milk can, and the ice inside this inner cylinder. And then there is a cap over it for heat insulation. Yeah, we have here our PV panels. 3 of them are enough here. 600 watt peak power, which we apply for one system. We have a battery for energy storage and our freezer, to produce these ice cylinders in the refrigerator. And a new thing is here a fan in the refrigerator to increase the heat exchange between the side walls and the ice blocks. Such a fan is highly efficient, and improve the efficiency of our system tremendously. The ice blocks are put in the cylinder. Cylinder is brought in the milk can, and the milk, surrounding milk, is cooled down. Okay, why using a battery? So we can collect here solar energy, but there is a surplus during the day, and this surplus is stored in the battery and then used in the evening hours, and then we can use all the solar energy to produce the ice. You see then here the system, the ice cylinder in the milk can, and the temperatures. Above here the line is ambient temperature, 35 degrees, Tunisia, very hot here. And if we apply 6 kilograms of ice for 30 liters of milk, we can cool it down here to, let's say, 70, 80 degrees very quickly, and this is enough to stop the propagation of microorganisms. Recommended is 4 degrees, okay, but we have seen, okay, this 16, 17 here is enough. If we apply 8 kilogram ice to 20 liters of milk, then we even can bring it down below 10 here, and then it's heating up slowly again over 12 hours. So the aim is to have here a transport window of, let's say, 4 hours to bring the milk from the farm to the collection station. And the second aim is to use the evening milk. Okay, farmers are milking 2 times a day. In the morning, no problem. So after maximum 4 hours, they have reached the collection point. But what to do with the evening milk? So it's too long overnight here. And this milk is either consumed by the family or even fed to the animals, because you cannot sell it if you cannot cool it. And therefore the green line, we also have been interested in longer cooling periods, 12 hours overnight, to sell it to together with the morning milk in the next day. Okay, and we do it in different locations here. Tunisia you have seen. Meanwhile we have further projects, for example in Kenya. And what we see here are the climate conditions. We see here daily horizontal irradiance, kilowatt hours per square meter a day. Tomorrow you will hear much more about that. And we see the other axis, the daily ambient temperature from 5 to 40 degrees centigrade. And to see the points, those are the combinations of temperature and radiation which we are measuring in those locations, and you see it's very different. So Kenya has a very narrow band of conditions, the blue ones here, whereas in Tunisia it's really wide scattered here, those combinations of temperature and radiation. There can be days here where we have high radiation but low temperature in Tunisia, maybe in winter times here. Or here days with low radiation but still high temperatures. So desert climate here, still warm in the environment. Whereas here in Kenya, tropical climate, very narrow conditions here, always here around this 20 degrees centigrade, it's a bit on the highland. And then we also have here these lines or colors for different ice production. Kilogram per day, how much ice can we produce with our 600 watt peak PV power? And we can produce, of course, most ice here in this corner. Why can we produce much ice in this corner and not in this corner? Okay. We have here high temperature and low temperature. That means we don't have to cool so much against ambient temperature. But this is only one part of the truth. There is a further one which you don't know, I assume. Maybe you surprise me. High radiation, low temperature, photovoltaic energy. You don't have to know it, and I don't tease you too long. So the efficiency of photovoltaic panels is higher at lower temperature. Very interesting. So if you're in a cool climate, you have a higher efficiency of your PV panels, and this is a second reason here. Okay. So, and then Victor, for his PhD work, made nice calculations. And he has here curves for reliability. How reliable is a system? How high is a probability that I can produce the required amount of ice? Can be very high, 90, or can be very low, 10%. And it's a matter of PV power installed. How much PV modules are we investing? 200 watt, 4, 6, 800. And the battery. It's a payoff between battery and PV panel. And this makes also the price. Those are here lines for same price. This is an expensive system here to have more than 90% probability that you produce the very right amount of ice. So he decided, okay, we go here to the 90% line, and we are investing the 1,900 euro here, and then we can see, okay, the best combination is 600 watt here and 1,650 watt hour of capacity of the battery, and then we have a well-working system. Well-working means to keep the microbial load low. You see the blades here, the counts of microbes here. The fresh was already the 600,000 colony forming units per milliliter. And then we had here cooled and uncooled condition. We are milking with 37 degrees coming out from the cow. And then the milk is cooling down slowly in this hot climate, the red line here. The black one is ambient condition. In that day it was 25 going up to 30. But you see the cooled milk, which is fastly going down here to this 15 degrees centigrade. And here you see on the right the effect on the microbial count. It went up to 3 millions. Uncooled, and we still have the 630,000 here for the cooled one. Fine. Okay, we have kept the microbial level. Down here we see the evening milk condition, long time storage here. It was a good milk, just 10,000 colony forming units here, quickly cool down, a lot of ice for a low amount of milk. I think it was 20 kilogram, no, 8 kilogram ice for 20 liter of milk. Cooling down quickly here, keeping the low temperature, and also the microbial load was just 15,000 the next morning. In that case, we don't have the comparison because we know this milk would have been spoiled. Yeah? Don't have to measure it, it's clear. Okay. Yeah, to the economics, to see such a system. Yeah, and you see here the retail price in Germany would be 2,700 euro, that's something for a farmer. And we see it's spread over PV panels, the batteries, yeah, the refrigerator, but also the milk cans. Yeah, also the milk cans make here 19% of the costs. But if you now bring such a system to other countries like Kenya, the price is going up to 4,700. And if you go in the pie chart, you see now the shipment costs. Yeah? Or even the solar system, the local solar system here also makes a high contribution here because solar systems are more expensive in Kenya than we can buy it in Germany. Yeah, and you have to take this in mind. Yeah, you cannot just look on the costs you have in your own country. You have to look at the costs at the target country, which is here the 4,700 euro. And this shows that we have to work here on this figure, that we have to produce the system locally, and this is what is now done in projects, yeah, to make it cheaper, also for countries like Kenya. You see other locations. Yeah, Tunisia has 10 systems. This was our first location where we started with the research, then followed by Kenya in 2 different locations with together 5 systems. Yeah, you see, by the way, here how the milk is transported on a motorbike from farm to collection point. And you see one of the latest projects here in Colombia with 4 systems, very close to you, not far away from Costa Rica. Okay. Yeah, for milk cooling, I also have 2 videos available. Maybe not bad to have a look on it. Showing the equipment. Yeah. Oh, it's already running. Yeah, you see the electronics, which are also developed in our group here. Yeah. Refrigerator is a DC refrigerator, not just a conventional one. Yeah, dual current. You see the plastic cans inside filled with water and then later being ice. Yeah, now the cylinder is fixed in the milk can and the ice block is filled inside. And then isolated by this cap. And the further video. Yeah, there's also software for it here. And now we are simulating here the climate for any location in the world. Yeah, this is done here by this system simulating a PV module, yeah, giving the current and voltage as we would expect in Tunisia or Kenya or wherever, and also in this room we are simulating the ambient conditions for the refrigerator. The ice inside, we are measuring, of course, many things. Okay, and so we can make simulations for any location worldwide. So, back again, and we are leaving now the big cooling. And I show you now very briefly solar drying, because we talk about this tomorrow, our whole day. Yeah? But it would be just missing when I wouldn't talk about that. Here is our most famous solar dryer, the solar tunnel dryer type Hohenheim. This is really developed since many, many years. As an MSc student, I already worked on this system here, and now it's commercialized in many countries in the world. You see this tunnel? So in the height of a table, and you see here the first part is a solar air heater. We have here a cover with transparent plastic film, and on the bottom here we have a black tissue to absorb solar energy. You can operate it by photovoltaics, fans sucking the air in, blowing through the tunnel, and those fans are operated by photovoltaics, so you are independent from the grid, can operate it anywhere. And then in the second part, we are putting our drying product, might be banana or apple or medicinal plants, many things are dried, meanwhile in this solar dryer. But it is a bit of expensive. It's commercialized. There is a spin-off company from Hohenheim and really selling the system. And too expensive for stable crop like rice. Yeah, very fine for high-value crops like mushrooms and fruits and vegetables, but for rice, which you just can dry along the road, like here in the Philippines, yeah, we needed low-cost version, and this is the low-cost version. It's only a tube on the ground. There is one, the bottom side is black plastic tissue covered by a transparent plastic film. Again, the solar panels to operate the ventilators, and inside we have the paddy. And you can open it just by a zip. Yeah, there was then a company having the system to apply such zips on plastic film. Yeah, and so you can open and close it very easily. And the problem is to mix the material. If you dry something in the sun, you have to mix it once in a while, and always to open the dryer and to do it is very laborious. And here farmers developed a very intelligent idea. And this I'm showing you in the next slide. Watch very carefully how it is mixed. You see two people here pulling here this pipe below the black bottom layer, reaching the end, coming back again, and you see how the paddy is hopping over the pipe. Coming back again. So a very intensive mixing system, very quickly, very intelligent, and invented by farmers. So we like to work together with local people. And the nice thing is that you can just roll together the dryer after you have used it, and you can store it somewhere under your bed. And then apply it next time when you need it. Okay, but as I told you, we have much more about solar drying tomorrow. Okay, so we can come to the next corner of our pyramid here, the energy. And we are dealing with rural energy provision. And first, again, some figures. You see here CO2 emissions here per capita worldwide, and you see that just in the tropics here, this figure is very low. So there are other nations like Europe here, like Russia, like Australia, like Northern America, who are contributing much more to CO2 emissions in our planet. But climate change is also hitting here population in tropical areas. The greenhouse gas concentration, we see that those curves are going up here since the Industrial Revolution here. CO2 ppm here is rising. We have now reached 400 ppm. When I was at school, we still learned 300 ppm CO2. Okay, but also other greenhouse gases like methane here is also highly greenhouse active here, and N2O, nitrous oxide here, and those are also coming from agriculture. Yeah, you see the gray parts here are coming from fossil fuels here, cement production and so on, industry. And the green parts here, they are coming here from forestry and other land use change. When we are changing forests here to agricultural production, we are releasing carbon from the soils, land use change, and those are the amounts on the bottom line. The line part here is coming from industrial processes. And this is rising temperature. We hear this frequently here in the media here. Temperature rise and also sea level change, and the sea level is rising, of course. Why sea level rising? Why? Ice is melting, yeah. By melting of ice, sea level is rising. What do you know about sea level rise in Costa Rica? Any topic here in Costa Rica in the media? You are discussing that? You release coastal lands, and very typically coastal lands are fertile and are very densely populated. People can have fishery and can have agriculture, so those are really the best locations, the coastal regions, and they will be lost here by sea level change, by sea level rise. And this has to do with energy, because of energy production, we have increased CO2 level in our atmosphere. But let's have a look if energy supply also has something to do with development of regions, of nations. And here I have a chart with one axis, the gross domestic product in US dollar per capita. And I have a second axis here, the energy supply in tons of oil equivalents, TOE, per capita. And we see that the dots are somehow going from left bottom to right top. And this is somehow giving the impression, okay, the more energy is available in a country, the more gross domestic product is produced, or the other way around, the more gross domestic product is there, the more energy can be used for that. And indeed, we see here different groups of countries. Here in this field, I have here industrial countries like Hong Kong, over Japan, Australia, USA. And we have some rising economies. Here the green ones here. I also would count Costa Rica in this region, Brazil, China, Malaysia, South Korea. And we have developing countries like Benin and Indonesia. And indeed, you see that here in Benin, Indonesia, gross domestic product is low, and also energy supply is low over there. Okay, that's one part of the message, but the other one are those lines. I have now drawn here a line through Germany, and I have drawn a line to Costa Rica. And we have here different inclinations. And what would you tell me about those inclinations? What is expressed by the inclination of this line? Is it better for society to be on this side of the line or on this side of the line? You mean down there? Yeah, I agree. We should be more down there. Okay. We also can make it mathematically, tangents. Yeah, we could go to Germany. Okay, this here is the energy supply. Yeah, per capita. And if I divide this here by the gross domestic product per capita, it's nothing else than energy supply per gross domestic product. And that means here the inclination of the line shows here the energy input for the gross domestic product. And not so bad for Germany. USA is much worse here. Yeah, China is a tragedy going here. But Costa Rica is a good example. You see the inclination here is lower than the one of Germany. Same as Hong Kong. Yeah? Same relation of energy input and GDP, gross domestic product. Yeah, Hong Kong lies down here because they have a lot of third segment, of service delivery. Yeah, this doesn't need much energy. I need a laptop and I can make bank transactions. Yeah, I can make a lot of GDP by that without much energy. If I am producing steel or so, then I need a lot of primary energy in my production to earn my GDP. So I wonder a bit here why Costa Rica is such fine here. Good message. Okay, so you're producing your wealthiness here with a low input of energy. Okay. Yeah, and all this energy use is still increasing. You see bottom line, crude oil, coal, natural gas, nuclear energy, hydropower, biomass, and then here renewable energy coming up here now and also increasing. And it's a bit surprising that biomass here and hydropower here are not counting to renewable energy. So those are the new renewable energies like wave power and photovoltaics and solar energy and all those new kinds of renewable energy. Yeah, how is the renewable energy share worldwide in total energy consumption? How much percentage? Here the colors, here dark green 50% already renewable, and then we see, wow, Africa is really leading. Yeah, so very high amount of the energy is renewable. Also Costa Rica is very nice here, dark green. Okay, and for Costa Rica I agree because you have hydropower. And it's really known that you have a very high share of renewable in your energy mix, at least in the electricity mix. But what about Africa? How can we explain that? Why has Africa here such a high amount of renewable energy? Yes. Very good, very good. If you grow trees as solid fuel to burn it, this would be renewable because you replant. But what is mostly not done is the replanting. Just deforestation, just cutting trees. Yeah, if you go to the map in Africa and you look the surrounding of cities or villages, they are deforested. And people have to make longer and longer ways to get the firewood. And this is not sustainable, but it is here counting as renewable energy. You always have to look for the source here. Oh, this is the International Energy Agency. Should be reliable data, okay, but they are counting here this biomass as renewable energy, which we call the traditional biomass. Traditional biomass. And we see more about that. Yeah, we see here traditional biomass. Yeah, firewood used in the kitchen. The kitchen is mostly a separate building, also called dirty kitchen, because of so much smoke. full of smoke. You see the walls are black here, but also the lungs are looking alike. Yeah, because women and children, they are spending much time here in this kitchen for cooking. And you see this is creating here cases of deaths, yeah, here in millions here. And you see it's 1.3 million, yeah, just behind tuberculosis and AIDS. So this is really a severe problem, this indoor pollution where people are relying on traditional biomass, 2.4 billion of people. Yeah, it makes about 10% of the global energy consumption. And up to 90% of this energy is lost by very inefficient combustion. Yeah, and this is even creating products of incomplete combustion, gases which are climate relevant. We see it here, different traditional fuels amongst modern ones. We have here dung. This is also part of traditional fuels. Dung is burned in Africa. In Ethiopia, it's very important. The dung is collected, made to cakes, and then sold. And you see here, during combustion, we are releasing here a lot of here methane, for example, yeah, or other non-methane carbohydrates here, and also plant residues here. Here, when wood is not replanted, that was your comment here, then we are adding here CO2 because it was first sequestrated in wood, but now we are releasing it. So if we replant, the balance is much better here, yeah? Replanted wood here. Kerosene, here LPG, and here on the bottom biogas, which has here very good balance here, very low amount of CO2 emissions during combustion. Yeah, but what are people using? So we have a kind so-called energy ladder. Here to the right, the prosperity of families is growing, and here on this axis, the comfort is growing. And here in the origin, we have crop residues and dung. So if people are very poor, they are using the crop residues, they are using the dung, not very comfortable, you have to collect it. You have this incomplete combustion, you have this smoke in your kitchens, and these residues are missing in the field. This is valuable fertilizer, this is nitrogen, this is phosphorus, what you are just burning. Yeah? You have ash at the end, you have some minerals, but you are losing your fertilizer. Then we have here wood, we have charcoal, coal, kerosene, ethanol, LPG, and at the end we have electricity. That's what we in Germany are using for cooking. What are you using in kitchen? Electricity or gas? Both? Okay, these ones. Okay. Yeah, you see here wood as fuel. You see here those kerosene stoves and here LPG stove. Yeah, okay. What are we doing? We are using plant oil for those rural situations. Yeah, we know that plant oil is also food, but there are minor qualities, yeah, and people have access to it in rural areas, in villages. Yeah, so we are using here biomass for energy, and this is such a plant oil stove. Yeah, so looks nice. It was a project with industry, with Bosch Siemens here. There is a vessel with oil, and you bring, here is a vessel with oil, and you bring pressure on it, so the oil is going here in this device, in this spiral here, and first you heat it, you put here some alcohol, some spiritus, and then you heat the system, and then oil is pushed through it, is evaporating, and the vapor is coming out here through a nozzle, and is burning here. And you have here a very efficient stove. You see here blue flame, yeah, the flame of this stove, and you see here the rural version, not the polished one. Here, so it looks here then in villages in the Philippines, for example. And you see here that we can reduce the emissions here, carbon monoxide, hydrocarbons tremendously here with the plant oil stove. Very clean combustion process, nothing against. Really good working. We tried different oils, sunflower, cottonseed, palm oil, jatropha oil, coconut. Yeah, jatropha was a hype because this is non-edible oil, and okay, we also got money for the research, but we focused not only on jatropha, we tried different oils as fuel for this stove. I will see here infrared image, very high temperatures of the flame here, but the problem is that we have here those residues inside the spiral. This one is opened, yeah, it's cut in two halves here, cut off, and here inside we have those residues, and you have to clean this stove regularly. Yeah, then here you see what we are pulling out. Here 3 are operated at the same time, yeah, to make experiments, replicates, and we are collecting here the residues, and this was our aim, to find the oils which are producing less of those residues. And you see here there is a difference between refined and filtered oil. Yeah, if it's refined, not just filtered, we are reducing here the residues, and coconut oil is producing less residues, for example, than sunflower oil with a high amount of unsaturated fatty acids. Okay, so it's working well, but it needs here introduction to workshops. You have to teach blacksmiths how to produce here those stoves, and you also have to give here demonstrations for the population. And you see by this drawing, it's not so easy. Yeah, you see a lot of drawings here. Yeah, how to clean the system, yeah, how to preheat the system, and therefore people are a bit reluctant to use it. It's too complicated. Yeah. Works fine, but still quite complicated. Okay, let's come to another aspect here for rural energy provision, and this is biogas. Yeah, if we produce biogas from the biomass, we are even producing biosludge, which is the effluent of the fermentation, the rest. Yeah, still valuable. Yeah, still our nitrogen is there. Yeah. Carbon has left. Carbon is converted to biogas, and the other things are still there. And so we can reduce emissions here. And you see our lab equipment. We have different lab facilities. These are the smallest one, just small syringes here. And we are putting different substrates inside, keep it on a constant temperature, 37 degrees. And the cylinder is rotating, and so the material is gently mixed inside. Yeah, and this has then a period of 30 to 60 days, depending on the substrate and temperature conditions. Normally 30 days for 37 degrees centigrade. And we measure then the specific methane yield, liters of methane per kilogram of volatile solids. Yeah, volatile solids is organic matter in your material. Yeah, this which can be transferred to energy. The rest are minerals. And if we compare the residues, rice husk has a very low amount of gas. Yeah, also pig manure, not a very good substrate. But now we are coming to cassava peels, not so bad. Yeah, 300 liter per kilogram. Banana peel, nice product here. Cassava pulp. Maize silage. This is our standard feedstock in Germany. Yeah, maize harvested green and then chopped, preparing silage, and from this silage you can take every day for biogas production. But also here citrus pressings. We have a lot of citrus here. in Costa Rica, and maybe a problem with the waste. Look here, the pressings have a very high specific methane yield, higher than maize silage, and if you just take the citrus seeds separately, it's really high. It's here coming close to 800 liter per kilogram. Because of what? Why? Hypothesis, the seeds of citrus. Oil, fat. High fat content, okay, energy rich, and this makes biogas. Yeah, but we also did it with coffee waste. Yeah, we have here coffee processing, here the wet method. So coffee is pulped, fermented and washed and dried, peeled and polished, and then we have the green beans and we have the byproducts. We have the pulp, we have the mucilage, and we have the parchment here. In the wet method, the dry method, drying the whole cherry, and then hulling, and we have the husk, everything in the husk, and the green beans. So our PhD student, Bill Hadde, here he analyzed here these 4 fractions of coffee processing byproducts. Husk, pulp, mucilage. And we have applied different temperatures. Yeah, 37 is standard, but we went down also to 30 and to 21, and therefore we applied not 30 but 60 days of time, 60 days of fermentation. You see here 2 lines, sorry for that, because we applied 2 models. This is a logistic model and this is the Gompertz model, forget it. Focus on 1 line. But you see the points are measurements. Yeah? So after a certain interval of days, yeah, we measure, okay, and then we make a model through it. Okay. The story is, for the husk, we have here a quite low amount. Yeah, if we apply high temperature, it is very quick, yeah, rising here during the first, I don't see, 10 days. Most of the biogas is produced, and if we have a low temperature, 21 degree, it's a slow process, and even after 60 days, we have not reached the full potential. There is still some to go, some left. Why do we do this? Why do we work with 21 degrees centigrade? Because in an industrial biogas process in Germany, the fermenter is heated. Yeah, there is a heating system in the fermenter, and we have heat available. We have waste heat. We are producing electricity from the gas, and the motor and the generator both have waste heat, and we take this heat to heat the fermenter. No problem. And then we can go to 37 degrees centigrade. Fine. But we are working also for locations like Ethiopia. And there we are in the highland. Yeah, and sometimes there is cold. Yeah, this 20 degrees centigrade, around 20. And then you have the heat. And this is, of course, a no-go. How shall you heat a fermenter in Ethiopia? Yeah, okay, we also try it with solar collectors. Can be done. But also difficult because the night is long, yeah, and how to keep the high temperature. And therefore it was for us very interesting to see how an unheated fermenter will react. Yeah? And therefore we worked with different temperatures. And under scientific aspects, it was really a lucky situation for us because nobody did it as we did, that we make a model which is also which also takes the temperature as an input. Fine for us. Now we have models, and we can also draw the lines for all temperatures in between. And slightly we can extrapolate, slightly. Okay, therefore we are so excited, yeah, about different models to find the best one. Okay, you see that mucilage here, like we have seen in the table. What did we see? I don't know. But now we see that mucilage here has the highest methane yield, higher than pulp and higher than the husk. Here we see the tables. Yeah. You see now here for standard conditions, 37 degree here, we see our specific methane yield, SMY, and you see here the parchment scarcely produce biogas. But if producing biogas, the methane content is high. Oh, by the way, biogas is always a mixture of CO2 and methane, so 50-50 roughly. But you see here for parchment we have a very high methane content of the biogas, but the yield itself is low, just 30 liters here. And then our PhD student here, he also calculated here the methane energy content in megajoule per kilogram of volatile solids here, and the energy recovery, and you see we can recover from mucilage here 66% of the energy which is inside. We can recover as biogas. The rest is then still in the effluent. There are still carbons, still could be burned if you would like. Much too valuable because it's a good fertilizer. Yeah, and then we made a calculation here for husk pulp and mucilage here, the residue production here in Ethiopia, what could be created here in terms of methane, what could be done with the methane, electricity and heat. Yeah, you could generate electricity here and heat, and if you also could use the heat, you are fine off, but we just calculated with the diesel equivalent, how much diesel would it be, and what is the cost of this diesel, and we have been surprised ourselves. It makes close to 30 million US dollar of value. So much diesel equivalent you could get if you would convert all the husk of Ethiopia. This is illusory, of course. Yeah, it's a potential analysis. What would be when all the husk would be converted here to energy? Okay, and also for pulp, 10 million, and for mucilage, 2 million. So that's really something. And the good thing is that coffee production is quite centralized in Ethiopia. So it's not so illusory to get most of the material for energy production. It's not so scattered like maybe in other settings. Ah, that's the same thing, just in ice, I see. Sorry, I didn't skip the other one. Okay. Yeah, and now, so finally, I come to a project on biogas, which I like very, very much. Yeah, normally we work with, industrial, I call it industrial, biogas plants, which are produced by industry and then operated by farmers. We have a good industry for that in Germany. But we are also working for locally adapted systems, and this is one of it, a very small scale system based on a plastic bag. This is a plastic bag, this is the cross section. We have here an inlet. The material is loaded here. This is dung from animals. It's produced for and in Ethiopia, and it's digested here and then goes out at the other side here, and it's covered here by a small greenhouse to heat it. Yeah? You know now the problem of heating. Here we do it with just such a cover here, and it works in Ethiopia in lower elevations. And we see here the system, how it is mounted. Here we have our black plastic bag here, and we have here Katrin Pütz. She is the one who is doing this development in Ethiopia. The inlet pipe here. And now in the background we see the greenhouse inside the plastic bag. In that location it was not a black one but a white one here. You see green coming out the tube here with a biogas. This pipe is to fill the system, and this is very special. This one is a bag where the biogas is catched. And this is really innovative. Normally such a biogas plant is directly combined to the kitchen, and people are using the biogas in the kitchen for cooking or for lighting. Yeah, but if you want to earn money with it, then you have to find a way to sell it. Yeah. And the idea was, okay, to fill those plastic bags. You see here 3 of them. And by the plastic bag, the biogas is transported. Yeah, this lady buys a load of biogas and brings to her home and connects to her stove. Yeah, inside is a stove. This is also a special development. You see, it's very simple here. Just pipes and this corrugated plate here, and the biogas is coming out here, and you can even bake this injera bread, yeah, this round bread, typical for Ethiopia, on it, and just some weight on the back, and the gas is pressed inside. Okay, and this works. Okay, and then coming now to more or less the end here. We also make life cycle analysis, yeah, for our developments, and we calculate here certain aspects of this balance. For example, here the primary energy demand is PED, megajoule. Here we have the GWP is a global warming potential here in kilogram of CO2 equivalents here per functional unit, which was 1 megajoule of heat. In this case, we have compared biogas and dung combustion. The eutrophication potential, the acidification potential. Eutrophication means how much phosphorus is brought to the environment. Eutrophication. Acidification, sour. Calculated here in SO2 equivalents. And this is the human toxic potential here. And the terrestric toxic potential. This is a chemical here which is here used as a standard. Okay, to understand the axis here. As I indicated, it was interesting to compare what are the consequences for environment when we produce biogas from the dung, or if we burn the dung directly, what is now done in Ethiopia as a standard situation. And then we have here different elements of the balance here. We have to construct a biogas plant. We might have methane leakage from the biogas plant. Always a certain percentage is also leaking. And this is 21 times more climate effective than CO2. The methane. From fertilization here, the biogas stove has to be produced. If we produce biogas, we have an energy credit because we are gaining energy. There is more energy in the biogas than in the dung because the efficiency of combustion is so low. We have dung drying credit because by drying of the dung, also methane is released, which is climate relevant. Dung combustion, if we burn the dung, we have a lot of greenhouse gases released, and fertilizer credit, because when the dung is burned, it's gone. But for the biogas, we have a valuable fertilizer. And we are replacing mineral fertilizer. So we calculate how much environmental load, all of those things, would be created by producing this mineral fertilizer. Okay. So if the bars are negative, it's fine, because then we have a gain. So that means here we are earning here in the energy production here. So it's much better to produce biogas than to burn the dung. And also, if you count here, you have more on negative side. That means you are releasing less CO2 in biogas use. For the eutrophication, it's a bit more here on that side. So we have a higher eutrophication because we are not combusting the material. We are bringing back the material. We are bringing back the phosphorus to the field. And so the environmental potential, of course, is then increased here. For acidification, it's 50-50, I would say. And for human toxic potential, we are much better here with biogas combustion because we don't have these poisonous emissions in the combustion process. The same here for the total environment, not only for humans. Yeah, and so Katrin is still working in Ethiopia, making such nice drawings here at the fence, where she's explaining to the people who are coming by here what she's doing and how the system is working. Yeah, here the small dome and the biogas plant inside, the biogas backpack, which is brought to the house, and the gas inside for cooking. Okay, so I am now coming maybe to the last slide here. Some conclusions here. Rural population can provide safe food under sustainable use of land and water. They are the agents in rural regions here to provide safe food. Rural population can also provide renewable energy. They are in the locations where there is water power. They are in regions where they can collect solar power. And we should not forget that. But the water, food, energy, climate nexus needs tailor-made solutions. You also have to know what is happening when you are turning one of the screws. Okay, so I would be through with this introduction. Do you have questions so far to the contents of all those things which I have pushed onto you? Yes. Okay, one